Hello, welcome to my talk on the voltage hysteresis observed during lithiation and delithiation of graphite, which is associated with different carbon stacking pathways in each cycling direction. So, primary motivation for this work is the fact that the open circuit voltage is a very easy parameter to measure. And it's very important in applications in control models. So, for example, in the control of determining the state of charge in battery management systems. One facet of this is still relatively poorly understood is that in certain systems, even after hours or even days of relaxation time, that a hysteresis is observed between the two cycling directions, whereas the OCV is usually interpreted as a thermodynamic parameter, so it's not obvious why this should be. There's an important gap in understanding as to what this metastable behavior could be caused by. And obviously, graphite is the primary alloy material in nearly every lithium-ion cell, but it's well appreciated that the open circuit voltage shows a difference between lithiation and delithiation. And that open circuit voltage is connected with graphite stages, so different orderings of lithium and carbon in the host lattice. And we can see, looking at this, that the features in the open circuit voltage are dictated by different lithium and graphite, different lithium carbon orderings. For example, the well-known stage 1 to stage 2 coexistence shows a coexistence of the same carbon stacking, that is AA stacking, but different lithium orderings. So in stage 2, you have alternate orderings of lithium in each alternate plane. However, this phase coexistence is dictated by orderings of lithium in different carbon stacking. So, for example, this dilute stage 2 occurs in AABB stacking. And this is important to highlight that these stages show different carbon stackings as well as lithium orderings. So the thought occurs that could it be that the difference in the open circuit voltage is due to a different pathway in the staging, and if so, why and how? So we found to our surprise that although the room temperature behavior of the open circuit voltage of graphite has been well explored, the temperature dependence hasn't been quite as thoroughly characterized. So what's shown here is the measured open circuit voltage at different temperatures during lithiation and delithiation. And you can see that there's an interesting trend in the temperature variation. So the stage 1 to stage 2 coexistence plateau shows relatively weak temperature dependence, but the other two-phase coexistence appears to show a systematic decrease in the open circuit voltage with temperature. And to our surprise, we found that no matter how much we increase the temperature within the experimental accessible range, that we get a residual hysteresis. So the lithiation and delithiation behavior don't converge to the same OCV. And we can understand a bit better this variation in the open circuit voltage with temperature by actually varying the temperature during the open circuit voltage relaxation. So this is a technique called entropy profiling. So to simplify matters, all of this entails is that in a GITT type experiment, so when the open circuit voltage is relaxing, rather than keeping the temperature constant, you probe how the measured OCV depends on the temperature. And the slope of the open circuit voltage with temperature gives you the partial molar entropy. And it's surprising, actually, that even this shows dependence on the cycling direction as well. So not only does the OCV, but so also does the derivative with respect to temperature. So we'll come back to the partial molar entropy hysteresis later. You can actually rearrange from thermodynamics, knowing the open circuit voltage and its derivative with temperature, you can actually also derive an enthalpy profile. And interestingly, this also shows dependence on cycling direction. So there's an enthalpy and an entropy dependence component to the hysteresis. To understand this energetic hysteresis, we have to turn to density functional theory. So these calculations were done by Chao Peng and Dennis Kramer in Southampton. And what this shows, so this was done done as a cluster expansion, that the ground state configuration for x less than 0.5 is AABB. And for x greater than 0.5, it's AA stacking. And our hypothesis, which subsequently validated, is that during lithiation, the host lattice follows close to the ground state configuration. But approaching from this direction, that due to energetic barriers to transition between the planes, the host lattice retains a metastable A stack configuration. And actually, this hypothesis is supported by examination of the interlayer carbon spacings, where DFT and results from inoperando neutron diffraction show the same trend for x less than 0.5. So we attribute this experimental enthalpy difference to the ground state structure following an AABB stacked host during lithiation, but retaining a metastable AA stacked host during delithiation. Going back to the observed entropy hysteresis, we can actually compare this result with calculations from mean field simulations, which I won't go into details here, but they allow lithium to be arranged essentially into two different levels. And you can solve a partition function to get all the thermodynamic variables out, so the entropy, the OCB, the enthalpy, and so on. So what's shown here is the configurational entropy in three different scenarios. So the first one is that the host lattice follows an ideal, not the host lattice, the lithium configuration follows an ideal solid solution behavior. And so this is quite a well-known result. This is where lithium fills the lattice randomly, resulting in a single maximum in the configurational entropy. Otherwise, if the lithium-lithium repulsion between lithium in adjacent layers is very large, then you would expect that lithium fills one layer at random and essentially a solid solution, and subsequently follows the next. And these two cases can be distinguished by an order parameter. So an order parameter of 0 means that you have random filling. And if the sign of the order parameter, if the magnitude of the order parameter is 1, then you have perfect stage 2 ordering. And of course, in reality, we have an intermediate situation, which we can model through mean field, whereby plugging in an interlayer lithium repulsion comparable with DFT calculations, you end up with a situation at 50% filling, where you have disordered stage 2 configurations, where you have a certain amount of interlayer lithium disorder in between the carbon planes. And so we can't only model this, we can actually determine this from the experimental data. So the raw partial molar entropy is quite difficult to interpret, but through an integration procedure, we can actually compare this directly with the mean field simulations. And the upshot of this is that, so the blue dashed line shows the post-process result for delithiation, The red one shows the result for lithiation. And you can see that this result suggests more interlayer lithium disorder during delithiation, actually agreeing quite well with the mean field result. And this result is also consistent with our proposed different carbon stacking pathway, because it's more energetically favorable to insert lithium into the AA stacked interlayers than the AB stacked interlayers, allowing more interlayer lithium disorder during delithiation. So, summarizing all of that, we've identified a residual hysteresis in the open circuit voltage at all temperatures, which has an entropy and an enthalpy contribution. We attribute the energetic difference to lithium remaining in metastable AA stack configurations for x less than 0.5. However, and that's during delithiation, during lithiation, the lithium follows something close to the ground state ABB stacked configurations. And we attribute the origin of this to lattice retaining some interlayer lithium disorder in stage 2 configurations. And this is actually supported by our entropy analysis, as talked about before. So I think this result is important not only for graphite, being the primary anode material in virtually every lithium-ion cell. I think for control models, this is simply something that has to be lived with and needs to be understood more. But the same methodology might also have implications for example, the insertion of silicon into graphite, which has increasingly been done to boost the capacity. And also the presence of silicon actually also increases the hysteresis. So I think this methodology is potentially applicable to a lot of other materials other than just graphite. So thank you for your attention. And if you have further questions, there will actually be a session at 12 p.m., 12 noon on April 29th.